this is the standard. This is the okay. This is the standard equation, standard transfer function for the two-pole system, and not just two-pole system. We have 1 0 also. If we have 1 0 at Z, one pole at P1, other pole at P2, then this will be the transfer function. So ADC is the DC gain of the opamp. So we got this big equation here. From this we have to find Z1, P1 and P2. So it is not very easy because this is very complicated equation. So we will make some assumptions and we will make simplified equation so that our design will be little bit easy. If we expand this, we can see DC gain into 1 minus S by Z divided by, it will be 1 plus, if we expand this, 1 be S into 1 by P1 plus 1 by P2 plus S square into 1 by P1 P2. So this term, this resembles you can see this is almost resembles our equation. We have the DC gain part, we have 1 minus S by 0 we have, and we have S square term, we have S term, and we have a 1. From this we can see that the S term consists of both P1 and P2, and S square term is 1 by P1 and P2. But after looking this, we can see this is the magnitude plot. So here will be P1. P2 comes after long frequency. So assume it is 10, then the P2 will be around 1000 or more than that, because this is in log scale. This is the log scale, and we know that these poles will be far apart. So yes, so we are focusing on the second term, that is S into 1 by P1 plus 1 by P2. That we can approximate as S into 1 by P1. When compared to 1 by P1, 1 by P1 plus 1 by P2 will be approximately equal to 1 by P1. When compared to 1 by P1, 1 by P2 will be negligible. For example, you take this example. So 1 by P1 will be 1 by 10 plus 2 will be 1 by 1000. So 1 by 10 will be 0.1 plus 1 by 1000 will be 1 milli. When this is 100 milli, this is 1 milli. So we can neglect this. So it is not the accurate value, but we can neglect. So from this you can say P1 equals the coefficient of S. Coefficient of S term will be 1 by P1. Okay, not P1. Coefficient of S will be 1 by P1, and coefficient of S square will be 1 by P1 into P2. So these are just assumptions, and we will make further simplification for this. So first we are going to find our P1. P1 will know it is 1 by the coefficient of S. So coefficient of S is R2 into Cc plus C2 plus R1 into Cc plus C1 into plus Cc into Gm2 R1 R2. That is R2 into Cc plus C2 plus R1 into Cc plus C1 plus Gm2 R2 R1 Cc. So we can say approximately this is the first pole. We can make it further simpler. Like if you see this GM2 or GMR is the gain of opamp. So not the gain of complete opamp, gain of one stage. So you can say this will be a big term, and again R1 will be in mega ohm range, and CC will be also considerable. But if you consider the other terms, all are small terms only. So you can say among all these terms, this will be dominating. So you can say this is approximately equal to 1 by GM2 R2 R1 CC. So this equation is important. This is the first pole approximately. So now we find now we have to find P2. So we know the coefficient of S square equal to 1 by P1 P2. So we have P1 P2 equals coefficient of S square. So from our derivation, we have the coefficient of S square is 1 by R1 R2 into C1 C2 plus C1 CC plus C2 CC. So this will be P1 into P2, but we want P2. So we can divide this by P1. So we can write it P2, the P1 P2 we are writing R1 R2 into C1 C2 plus C1 CC plus C2 CC divided by P1. So it will be, this is 1 by thing, divided by, then 1 by GM2 R2 R1 CC. So we can cancel this R2 R1 R2 R1. So P2 will be GM2 by C1 C2 plus C1 CC plus C2 CC. Among these terms, C1 is only the gate capacitance and the parasitic capacitance. So effectively C1 into C2 will be very small value. Again here also C1 into CC comes. These two will be very small. So, okay, one CC is missing here, CC. So we can neglect when compared to C2 into C2 will be a bigger one because it is contained in the load capacitance, and CC also comparable to C2. So this term will be very big. So these terms will be small. So we can neglect these terms, and we can write P2 will be approximately equal to GM2 CC divided by C2 into CC. You can cancel this CC. So you can say P2 is approximately equal to GM2 by C2. So this equation is also important. This is the location of the second pole. This is the location of the first pole. The first pole. This is the second pole. So this was our complete transfer function. From that we derived P1, P2 we derived. So what is remaining is DC gain and the zero location. So zero location is very straightforward. We have the standard equation here. This is the standard equation. Zero is what is coming the denominator of the S term. So here it is GM2 by CC. So the 0 we have, 0 is equal to GM2 by CC. And first pole P1 we have 1 by GM2 R1 R2 CC. P2 we have GM2 by C2. So these equations are the important equation that we derived in this section. Now what is remaining is DC gain. So DC gain equals, see, when all the S term is 0, then what is remaining is the DC gain. If all the S term is 0, then there is nothing in the denominator except this one, and in the numerator we have GM1R1 into GM2R2. This is the DC gain of the operational amplifier. Okay.